Our integration tools will come from reversing the rules that we learned in differentiation. This tool, called integration by substitution, or sometimes U-substitution, is done by reversing the chain rule. Now I've written the chain rule below so that we can see it easily. Now let's throw an integral on each side. I'm going to start here with the indefinite integral, but I'll show you how to deal with the definite integral a little bit later on. Now the indefinite integral here is asking us to find the antiderivative of the derivative of f of g. And that's a bit of a mind bender, but if you think about it for a bit, you'll see that f of g of x is an antiderivative of the derivative. Okay, but how do we use this in practice? Chances are any integral that we're given isn't going to be nicely formatted like the left-hand side. The easiest function to identify is g, since both it and its derivative show up in the integral. Having done this, we'll define a new variable u to be equal to g of x, and we'll set du to be g prime of x dx. Now, this probably looks a little bit weird, but to help remember it, note that du dx is g prime of x. So if we pretend that we can multiply both sides by dx, we get precisely this statement. So now we're going to take that and plug it into the integral. Our goal here is to convert all of the x's into our new variable u. If we've done everything correctly, then our new integral will look like this. Now this new integral is much simpler to evaluate, so we can integrate it and convert back to x. In practice, we might still have to find an antiderivative of the remaining integrand, but the hope is that the integral will be easier to solve. With all that said, the best way to figure this out is to see it in practice. So let's integrate the following function. First thing, we're looking for a function and its derivative. Pause the video if necessary, and see if you can identify what g should be. In this case, I see an x to the 4 and a 4x cubed, so let's set u to be x to the 4 plus 3. You don't have to include the plus 3, but since it doesn't affect the derivative, including it will make our lives a little bit easier. Du is 4x cubed dx, and so subbing this into our integral, we get the following. And you don't have to do this part, but I'm actually going to rewrite the integrand so that we can see how du comes into play. The result is an integral that only depends upon u. And it's fairly simple to find an antiderivative of u to the power of 20. And changing the answer back to x gives us our final solution. In this case, we got lucky, right? Because this exact derivative 4x cubed appeared. In general, we only need to get close to the exact derivative. So for example, what would we have done if that 4 hadn't appeared? Let me show you with another example. Let's find the integral of this function. Again, take some time to identify what the substitution should be. Now I'm going to take u to be x cubed, so that du is 3x squared dx. The x squared part shows up in the integrand, but we don't have the 3 that we need. Turns out there are two possible ways to handle this. In the first method, we'll rewrite our expression for du to isolate for what we do have, namely the x squared term. In this case, I'll divide everything by 3. Now we plug everything into our integral, and once again I'm going to rearrange things just to make it easier to see where the du appears. Note that instead of just du, we get du over 3. At this point the rest isn't too bad. An antiderivative for e to the u is e to the u, and if we take all that and convert it back to x, we get e to the x cubed plus c. In the second method, we add the 3 that we're missing to the integral. But of course we don't want to change the integral, so when we multiply by 3, we must also divide by 3. We now have the 3x squared term that we want, so substituting this back into our integral gives us exactly the same thing that we had above. Both methods are mathematically identical, and there aren't any significant differences in terms of easiness, so just stick with whatever you like best. Finally, we move on to definite integrals. We're going to start by noting that f of g of x is an antiderivative for f prime g of x g prime x. Thus, by the fundamental theorem, we can evaluate this integral by plugging in the bounds of integration into an appropriate antiderivative. On the other hand, when we make the substitution u equals g of x, the integral changes. I'm just going to write top and bottom for the bounds of integration because we don't know what they should be yet. An antiderivative for f prime, though, is f, so by the FTC, we get f top minus f bottom. If we want these to be equal, we can see that top should be g of b and bottom should be g of a. Hence, when doing substitution with a definite integral, we do exactly the same procedure as an indefinite integral, but we just have to remember to change the bounds of integration. Okay, one more example. Let's compute this definite integral. Seeing both x squared and x, we're going to set u to be x squared plus 1. This also makes du 2x dx. Since we're missing the 2, I'm just going to preemptively rewrite the du term. Now we need to evaluate how the bounds will change, so I'm going to plug the bounds into our new variable. This gives us out 2 and 10 as the new bounds. Plugging everything into our integral gives us the following. At this point, we go through our usual integral computation, making sure that we use the new bounds to evaluate the integral. The great thing about changing the bounds is that we don't have to convert the integral back into the variable x. However, if you did want to convert back to x, then you also have to revert back to the original bounds. In the example above, we go through our usual motions until we get to a point where we plug our numbers in. This time, let's convert back to x, remembering to also change our bounds back to 1 and 3. Doing so gives us exactly the same answer. And this can be very useful if it's difficult to find the values of your substituting function. So that's substitution, which is one of the most important integration techniques you can possibly learn.